My name is John David Bartow, and it's a pleasure for me to introduce our speaker this morning. I trust you all had an uneventful trip through the traffic to our convention center this morning. We've all heard about a rather spectacular traffic accident in space earlier this year. And for those of us like myself who are not experts in this field, it raises many interesting questions in our mind about what led up to this event, what was the outcome, are there any long-term implications? And we're very fortunate to have the right person to address us this morning on this subject, Mr. Nicholas Johnson, who is the Chief Scientist for Space Debris at NASA. Mr. Johnson has been in this field for 30 years. He's co-chair of the IAF Committee on Space Debris, also the co-chair of the symposium on that subject here at this conference. He's the U.S. expert at the United Nations and also head of the U.S. delegation for the Interagency Space Debris Committee. So I think we have the right person to talk to us. Please welcome Mr. Nicholas Johnson.
Thank you, John David, and thank you for the audience for coming out this morning, early in the morning on the last day of the conference. Hopefully, at the end of my remarks, you'll think that it was worthwhile to make the trip out here early this morning. As John David said, I think everybody is aware of the event which occurred early in this year, and what I'd like to do is give you a bit of a background on the event and its consequences, and also the implications for future operations in space, which not so much by coincidence will lead into the next plenary session at 9 o'clock. Although there have been other hypervelocity collisions in space, both intentional and accidental, this was the first time of an accidental collision between two intact spacecraft. And they were sizable spacecraft, which of course led to sizable debris fields, which we'll talk about in just a minute. And not coincidentally, it occurred at one of those regions in near-Earth orbit, which is the highest or near highest spatial density. And so from a probability standpoint, this is exactly the kind of activity you would expect to have a collision of this nature happen where there is great congestion in the environment. Iridium-33 was an operational U.S. communications satellite with a mass of about 560 kilograms. The other satellite was a non-operational Russian, by coincidence, communication satellite with a mass of about 900 kilograms. At the time of the collision, as I said, the Iridium spacecraft was operational, and it turns out that the way that we first found out that the collision took place was when that spacecraft ceased transmitting abruptly, and the operator of the system contacted representatives of the U.S. Space Surveillance Network and asked, did something happen to our vehicle? To date, the U.S. Space Surveillance Network has identified over 1,800 large debris from this event, large meaning larger than about 10 centimeters in diameter. About 1,400 have been officially cataloged by the U.S. Space Surveillance Network. The rest are in a mode of tracking and eventual cataloging. However, we have done special observations on the debris fields and have seen many, many more debris of a much smaller size. We'll talk about that in a minute, too. At the time of the event, it just by happenstance, the orbital planes of the Iridium and the Cosmos spacecraft were roughly perpendicular. It really does not make a lot of difference in the outcome other than the collision velocity, which far exceeded that for a catastrophic breakup. So here we have the event, and then the growth of the two debris clouds will show two full revolutions about the Earth. The debris very, very quickly expands around the orbit plane. And you'll see that after just two revolutions, almost all of the plane now is populated with debris. However, the debris doesn't stay in those nice little individual planes. You also see that twice a revolution, these debris are passing through one another. And that, of course, could lead to additional collisions between the debris. So this is a depiction of the orbital planes of the debris in June of this year, so several months after the February collision. And what this animation will show is how the orbital planes will propagate over the next 2 years. You'll see the red lines represent the Cosmos 2251 spacecraft. It has a lower inclination, therefore it has a higher differential precession rate, and the debris is expanding and dispersing more rapidly than the Iridium debris, which is shown in green. You have, as you might suspect, 2 holes at the poles, which are, of course, defined by the inclination of the respective debris clouds. And what you wind up with is basically a ball of twine. And after a year, and certainly at this point where we're now at 2+ years, you basically have reasonably randomly distributed debris all around the Earth. Now that is the dimension in terms of the right ascension of the planes. Then there's the other dimension, the radial dimension. How is this debris distributed in altitude? And what we see here is what we call a Gabbard diagram, which depicts the apogee and the perigee of every single debris which has been tracked and cataloged. And the red, again, depicts the Cosmos debris, and the blue or black, depending upon the sheet here, the Iridium debris. The Cosmos debris goes to greater extent, almost the entire or height of the LEO regime, up to about 1,700 kilometers. The dispersion of the Iridium debris is a little bit less. Interestingly, and again, this is probably not by happenstance, there are approximately twice as many debris from the Cosmos vehicle as from the Iridium vehicle, but there was about twice as much mass in the Cosmos vehicle in compared to the Iridium vehicle. Now, one of the questions which everyone asks is, oh, how long will that debris be up there? And so with one caveat, which I'll tell you, this chart depicts how the number of debris is going to decrease over time. Again, the red being for the Cosmos vehicle and the blue for Iridium. You'll see little stair steps in there. That is assuming that we have normal future solar activity. Many of you in the audience are probably aware we are very much away from normal solar activity right now. It's abnormally low. We keep expecting the solar activity to increase, and it has not. So this is a optimistic view at this point of what the debris environment will be in the next coming decades. If, in fact, solar activity does not start to increase as we used to see during the past century, then the lifetimes of these debris will be much longer. Now, you also see a distinct difference between the Cosmos debris and the Iridium debris. The reason for this is that the Iridium spacecraft was probably the first spacecraft to have had a severe fragmentation, which also was made substantially out of composite materials. Not completely, of course, but a great number of composite materials made up the spacecraft. Those materials have a higher area to mass ratio, and therefore they decay more quickly. And so, fortunately, within about 5 or 6 years, again, assuming we return to normal solar activity, we will have about half of the debris re-enter the Earth. So, what do you do to prevent satellite collisions? Well, the United Nations Space Debris Mitigation Guidelines recommends limiting this accidental possibility, if at all possible. And the guideline is indicated here, says if available orbital data indicate a potential collision, adjustment of the launch time or an on-orbit avoidance maneuver, if you're already in orbit, should be considered. This, of course, demands that you have some foreknowledge of not only your orbit, which you would certainly have, but also that of all the other space objects through your altitude. In the United States, these conjunction assessments are conducted by the Joint Space Operations Center, which is part of the U.S. Strategic Command. And I did want to make a comment here that the publicly available data, which the U.S. Distributes through a website to the world, is of a lower fidelity. And that data is really not sufficient to do precise conjunction assessments, certainly not on which you would base a collision avoidance maneuver. To date, there is no requirement for the U.S. to do conjunction assessments for all of the operational vehicles in the world. We obviously do those on a real-time basis for U.S. satellites, and I'll talk about that in just a moment. However, the U.S. does respond to requests from owner-operators wishing this type of service. It turns out that at the time, in February collision, the owner-operators of both the Iridium and the Cosmos spacecraft had not requested such conjunction assessments, so none had been made, and there was no forewarning of the potential collision. At NASA, we have been doing collision avoidance since 1988 for our manned spacecraft. Obviously, with human-piloted vehicles, we work very, very hard to preserve the safety of the crew and the vehicle. And even though the probabilities of collision with human spacecraft are relatively low because they operate at relatively low congested regions of low Earth orbit, we do these maneuvers. We do on a daily basis, actually typically 3 times a day, we conduct conjunction assessments to see what the next 3 or 4 days holds in store for us. To date, the International Space Station has conducted 10 maneuvers. Some of those maneuvers have been while the space shuttle has been attached, and the space shuttle have actually conducted the maneuver. If not, a progress vehicle which is attached would normally do that job. The space shuttle, when it's in an independent flight, has done 9 collision avoidance maneuvers, and the latest was just last month. Since 2005, NASA has started doing conjunction assessments for our robotic spacecraft. We operate, as you well know, a fair number of robotic spacecraft in low Earth orbit, as well as in GEO. And on average, we conduct 2 collision maneuvers per year for the entire fleet of over 24 spacecraft. So it's really not a frequent occurrence. However, it does turn out that we do the conjunction assessments and we prepare for maneuvers much more frequently but many times at the last 24 hours or so, we decide that the risk to the vehicle is not sufficient to warrant a collision avoidance maneuver. And in addition, for a robotic spacecraft, we are taking a slightly higher risk tolerance, where with human spaceflight, we typically maneuver if the risk of collision is on the order of 1 in 10,000. For a robotic spacecraft, we may accept a risk of 1 in 1,000 or slightly greater. The threat of debris from Iridium and the Cosmos debris is real. It is a threat to every operational spacecraft in low Earth orbit. NASA conducted one of the very first collision avoidance maneuvers due to this collision in April of this year when a piece of the Cosmos 2251 debris came close to our vehicle, or was predicted to come. The ISS recently was prepared to do a collision avoidance maneuver for another piece from Cosmos 2251, but we literally called off the maneuver within 24 hours of its execution after we had prepared the crew and the commands to do it, because we decided that it was going to come quite close enough to meet our thresholds of maneuver. However, as important as it is to do collision avoidance maneuvers for those items you see, the real risk to operational spacecraft comes from those debris which are smaller than the track population. Collision with any particle down to 1 centimeter, certainly for any spacecraft, is potentially catastrophic. But that's the unseen risk that we cannot handle deterministically. And some people always ask the question, well, what about insurance? Well, most LEO spacecraft don't have insurance. As I said, this is not the first time that we've had accidental collisions, and we actually had 3 previous collisions, and they happened to occur roughly 5-year intervals. But the three previous collisions have all been between a large object, an old spacecraft or an old rocket body, and a piece of smaller debris. And in those three cases, we did not see large debris clouds being created, which certainly is a good thing. But when you have two large objects colliding, even if they collide in what we call a glancing blow, we don't know exactly how Cosmos and Iridium collided in this event, you wind up with large numbers of debris. So what does it really indicate for the future? This is a statement from a paper published in Science in January of 2006, which talked about what would happen to the then current orbital population if there was never another launch around the world, just allowed the debris up there to gradually fall back to Earth. And what happens is for the first about 40, 50 years, you have sort of a steady state environment where small debris and large debris at low altitudes is falling back to Earth at about the same rate that collisional debris is being generated by these accidental collisions. However, after that point, the rate of creation of debris exceeds that of natural decay, and the population will continue to grow. Unfortunately, the situation now is substantially different because since 2006, when we did this first study, we've had two major accidents, this collision and another event in 2007, so that the rapidity, the frequency, the growth of the debris possibilities is now increasing even more. So what's the challenge? The challenge is to get rid of the sources of potential debris. There are over 4,000 derelict spacecraft and launch vehicle stages currently in Earth orbit, which are in fact simply future debris sources. NASA studies indicate on the positive side that if we could find a way to remove as few as 5 of these per year, that we could in fact stabilize the current environment. Many of these vehicles are concentrated in altitude, but they are not concentrated in orbital planes, so that raises additional challenges. Missions to rendezvous individually with old spacecraft and old rocket bodies are typically complex and expensive. And then at that point, you still have to effect some means of disposing of the vehicle after the rendezvous has been completed. There have been suggestions of using directed energy systems, for example, ground-based lasers, to somehow put vehicles into either higher orbits, which are less congested, or bring them into lower orbits where they would fall back to Earth more rapidly. That also has substantial both technical and economic challenges, and directed energy is normally not a very attractive solution for very large debris which weighs multiple tons. So in summary, unfortunately, this accident was the most severe that we've seen to date over these past 50 plus years. However, as we showed earlier, half of this debris, with any luck, will be down within about the next 5 or so years. Very few debris have re-entered to date. But some debris will remain through the end of the century and will present, again, risk to those operational spacecraft. And the negative side of the story is that collisions will continue. Collision rate will increase as time goes on. And by the end of the century, the collision rate will certainly be greater than once every 5 years. Thank you. That's great.
We have time for some questions. Who would like to start? Yes.
Hi. The question was, how do we track debris that actually asked smaller than 1 centimeter, but the real question is, how do you track debris smaller than 10 centimeters, where we currently have that capability? And the answer is, we can't do that right now. We actually have one sensor in the U.S. that can track some high inclination debris down to about 5 centimeters. But we do have sensors on the ground that can detect these debris. That's how we know what the populations are. But those sensors are not of a capacity and we have too few of them to allow us to do the deterministic type of catalog operations which we have for the large debris. So what happens is that you can avoid the 10 centimeter debris, larger debris, by simply moving out of the way, which we do. And if the debris is smaller than about 5 millimeters, it's typically not hazardous to the spacecraft, again, depending upon where you're hit. So the residual risk that we have to accept is that risk between the 5 millimeters and the 10 centimeters. So that's why over the last 20 plus years, the international community has been working so hard to curtail the growth or the creation of that kind of debris, because that's where the real risk of spacecraft is now.
Let me ask one first. Has there been any change in the number of requests for conjunction assessments as a result of this?
And the answer is absolutely. The United States has received many requests. We are sending out conjunction assessment messages to those operators which have asked for it. And in fact, we are sometimes sending out unsolicited conjunction assessments to owner-operators just to make them aware that we believe there's going to be a close approach. We are on record with the United States of trying to achieve a capability before the end of this year to be able to perform conjunction assessments on every operational vehicle in Earth orbit.
Yes.
Nick, when you mentioned removing 5 vehicles per year, does that assume that all future launches have some sort of disposal plan, and this is old stuff that doesn't?
All right. The answer studies both ways. We've done a study that says, what if we start removing debris, but the international community is not following the guidelines which have been developed by the IADC and United Nations? And then we've done the study, what if people are more compliant with those guidelines? And the 5 number is associated with a relatively high degree of compliance with debris mitigation, the so-called 25-year rule. Not absolute compliance, not 100%, but relatively high. If you believe that there's going to be a more severe non-compliance of the 25-year rule internationally, then it will take a little bit more than 5 per year to stabilize the environment.
Yes. Another question? Yes.
The collision between Cosmos and Iridium predictable and avoidable?
I believe the question was it predictable?
Predictable and avoidable.
And avoidable. It was predictable, and since one of the vehicles did have maneuver capability, potentially it was avoidable. However, you need to understand that even using our very best techniques in the United States, the conjunction assessments are not absolute. There was always a level of uncertainty. As I mentioned before, when the level of probability of collision reaches 1 in 10,000, we maneuver a human spacecraft, and 1 in 1,000 for robotics. So there's always an uncertainty. And depending upon your orbital regime, you may have many conjunction assessments in a short period of time. That is particularly true for Iridium. In fact, it is almost unique because of the 70-plus spacecraft they have operating at this single altitude, which is already very congested. So that we are now doing conjunction assessments for the Iridium Corporation, and I can tell you that there are many conjunctions every single day. And so you have to determine which ones are the highest probability, and it's a very delicate risk management situation that is, to some extent, a subject of simply judgment.
Another question? Yes, front row.
I know that in the same orbital path there were other 10 Iridium satellites. What happened with these Iridium satellites? Were they removed, that they were not Iridium 33 debris?
Okay. What about the other 70-plus satellites which are still operational? And, of course, the Iridium-33 was replaced within about 3 weeks because there was a spare satellite which were brought into its slot. Again, the many conjunction assessments which are calculated every day for Iridium, many of those are from debris from the collision. But I would say over half of the conjunction assessments involve objects not associated with a collision. So yes, the probability of collision, the risk to Iridium has increased because of this event, but the greater risk still resides in the resident space population which was already there.
Have they made any avoidance maneuvers at all since then?
I probably shouldn't answer this, but the answer is yes. Iridium has done some collision avoidance maneuvers. Sir.
Okay, we still have time for questions? All right. Well, if not, Nick, we certainly appreciate you coming this morning to discuss this with us, and I hope you stay for the plenary on similar matters. Thanks again, Nick.
Thank you.